Hello class. On week 5, in these guided notes we will primarily discuss the operations of addition and subtraction with whole numbers, but before we do so, let's talk about large numbers. Large numbers are a part of our daily reality. For instance, according to concordcoalition.org, the US debt was at one point estimated to be this very big number. Explain the quantitative meaning of each digit in this large number. And just as a side note, I will hold you accountable for being able to break down and describe numbers as large as 1 quadrillion. Let's talk about what these digits mean. I'm going to put them into this box from right to left. So you have a 5, a 7, an 8, then there's a comma. I'm going to put a bold line here to where the commas are in our number. Then we have a 0, a 4, and a 4, and another comma. So I'll put a bold line right there. 3, 1, 9, another comma. 6, 3, 6, another comma. And then 6 and 2. Now in this box is a 9, but this clearly does not represent just 9 as part of our debt here. This 9 is in a position. It has a place value, and it's more than just 9, even though the digit there is just 9. All right, so focusing here on the 5 position, the furthest right, this is how many ones we have. And the next box is how many tens we have. And the next box is how many hundreds. Oops, I didn't mean to do that. And then the relationship between 1, 10, and 100 is that we keep multiplying by 10 to go from right to left in our table here. So I could say this is how many ones we have, how many tens we have, how many hundreds, which is 10 squared. Multiply by 10 again, the pattern continues, it would be 10 cubed, right? That's how many thousands we have. And I'm not going to write out every single word of these, but we have 10 to the 4th, 10 to the 5th, 10 to the 6th, 10 to the 7, 10 to the 8, 10 to the 9, 10 to the 11, 10 to the 12, 10 to the 13, and the last one in this case is 10 to the 14. Let's actually go ahead and write out these numbers. 10 to the 4, that's a 1 with 4 zeros behind it, and it's a 10,000. So this is how many 10, I'll abbreviate if you don't mind, 10,000s we have in this position. The next one is how many 100,000s we have. 100,000s. After that we have 10 to the 6th, which is how many millions. Then we have 10 millions. Then we have 100 millions. After that, the next digit is the 6, is 10 to the 9th. That's how many billions there are. Then how many 10 billions there are. And then how many 100 billions there are. The next digit is trillions. Then how many 10 trillions, and etc. If there were more digits, the next one would be 100 trillions, and then the digit after that would be the quadrillions. So be comfortable with all of these words and these place values when breaking down large numbers. This is an extremely large number, and it's unfortunate that our debt is anywhere close to this. The next item here is item 2, where we talk about something called quantitative reasoning, or just quantities and quantitative relationships. Arguably the most significant contribution mathematics has made to society is our use of mathematics to model our reality. Mathematics is a valuable tool for measuring and comparing quantities, and for establishing quantitative relationships. In this class, I will use the term quantity in a very specific way. It'll be to mean the measurable attribute of some object or idea. Consider the image and statement below. So we have a picture of a bucket with some water in it, and let's say the size of the water's volume is 3 gallons. So the object in this of our focus here, of our quantitative focus here, is not the bucket, it's the water. You can imagine the bucket just disappearing and the water sort of being held there in place by some invisible container. I don't care about the bucket. I don't care about how much water the bucket can hold. I only care about how much water is currently in the bucket. The water is the object in our breakdown. We're going to do something like a sentence diagram to help you understand better how I'm going to be using this word quantity. The water's volume is the attribute. And volume, if in case you're not sure what volume means, volume is the amount of three-dimensional space taken up by something. So how much 3D space is taken up by the water, that's called its volume. And the water's volume is the quantity. Right? Look closely at how I'm using the word quantity. It's a measurable attribute of some object or idea. So the object is the water, or you can just imagine the water. And for example, all of us are imagining water right now because there is no actual water in front of us. We're pretending. So in this case, you could argue that the object is really also an idea. That's why I put object or idea. Something that you can think about or something that you actually physically have in front of you. You can also think of an object as a mental object. So an idea could be considered an object as well in that sense. So water is the object, and it has some sort of attribute, and that's going to be its volume, and the volume is something that's measurable. So the water's volume is the quantity here. Some people like to use the word quantity to talk about how big the volume is. So using the 6 gallons. But I'm using it more generally, more abstractly. Quantity is something that you can measure, and it's some measurable attribute of an object. For example, a person who is standing up, that person is the object, and then that person's height while they're standing is an attribute of that person that you could measure, and that would be a quantity. The person's height is a quantity. And of course, that height might change over time, or as they grow, or shrink with age, or it might be an unknown, we haven't measured it yet, or it might be known, you might know that the person is 6 feet tall. Anyway, back to the water situation. The size of the water's volume is what we're trying to measure. And we say that it is 6 gallons. We're going to call the 6 gallons the value of the quantity, or the value of the measurement. And if you want to break down the 6 in the gallons, we can say the 6 is we'll call that the numeral, and the gallons is the unit of measure. Or you can just say unit for short. Like when they say, don't forget your units, we're talking about the unit of measure. Or you can also call it the referent. It's the referent of the numeral. So quantities don't need to be measured in order to exist in your thinking. Like you can look at that picture of the water and have an idea that it takes up a certain amount of space, therefore it has a volume, and you can imagine it. Also, when you measure it, depending on what your unit of measure is, you might get different numbers, right? 6 gallons is the same thing as 24 quarts, right? Because there's 4 quarts in each gallon. And if you're doing cups, it'd be 96 cups. Or if you're doing liters, it'd be some other number, right? So 6 isn't the quantity here. 6 gallons is not the quantity here. 6 gallons is the result of measuring the quantity, and the quantity is the water's volume. Okay, I'm going to try to be as consistent as I can with this definition when I use the word quantity versus value of the measurement. Or sometimes we'll also say value of the quantity. So either the value versus the quantity itself. The quantity is what you're measuring, and the value is the result of that measurement. In general, numbers are meaningless. I'm now reading down here. Numbers are meaningless unless they are situated in a quantitative context and accompanied by some unit of measure. Consider the statement, John gave Jill 3. If I stop that statement right there, what does this mean? And give at least 2 interpretations. Well, let's give 3. Or I could say something like, John gave Jill 3 pennies. Right, here's one possible interpretation. We could also say three $20 bills. Right, in both of these cases, John gave Jill some sort of monetary amount, some amount of money, but the unit on the 3 made all the difference. 3 pennies is not nearly as good as three $20 bills. Or it might be there's nothing to do with money. Maybe John gave Jill 3 puppies. Right, so to have numbers when we're trying to talk about reality and you don't have a unit of measure on that number, then it's ultimately a meaningless expression. Every number needs to have a referent, something that it's referring to, or some unit of measure. Okay, now let's focus on addition. The quantitative operation of addition is the mental act of combining, or we could use the word joining or grouping together, 2 or more quantities. Now remember, quantities don't have to be measured. Like I could add your amount of money with my amount of money and not have either of those amounts measured yet, but still imagine that operation. This is what I mean when I say that quantitative addition is conceptual and can be imagined even if the quantities are not yet measured. Now when we talk about the numerical operation of addition, this is the combining of 2 numerals to form a new numeral. This is what most of you think of when you think of doing addition. It's just combining 2 numbers into a new number. Consider the following statements. Combine John's money with Jill's money. All right, so let's say John's money is represented by this block. And Jill's money, let's say she has more money. So I'll make a larger block. When I combine John's money with Jill's money, we put this little symbol plus sign. So we can say John's money plus Jill's money. And what's happening conceptually is that we're taking Jill's money and combining it with John's money and making a new amount of money. So symbolically it would look something like this. We would put a plus sign and put an equal, and then I would copy this and put this here, copy this one, put it there, and put them together, and we get a new amount of money, the result of combining the 2 amounts of money. So this operation is conceptual, and it didn't necessarily, I didn't need to know the amounts. Sometimes you could use letters instead, like A stands for John's amount of money, it's an unknown, and B stands for Jill's amount of money. And A plus B stands for the combined amount. However, if you happen to know John's amount of money and Jill's, and you know their units of measure, they're both $8 and $5, then we can do the numerical addition and arrive at a numerical result. Now in this case here, if you want to put units on here as well, just to show that we're mindful of the units, you would have combined, they have $13. But numerical operations are these that are often done in an abstract context, meaning we don't know what the units are. We just add 8 somethings plus 5 somethings, and we get 13 of that thing. Let's look at this one here. Notice that for numerical addition to occur, in other words, in order for me to get 13 here, the 2 values must have the same referent, which means the result would also have the same referent. This is what was happening when I put dollars on each of the 8 and 5, and then the result was also in dollars. All right, if I said, what's $8 plus 5 apples, you would not be tempted to say 13 of something unless you abstracted and said 8 things plus 5 things, then you could say equals 13 things, even if all those things aren't the same thing. The fact that we are just generally thinking of them as things, then it allows you to add 8 and 5 and get 13. But if you had $8 plus 5 apples, what would you say you had 13 of? I mean, you wouldn't be able to say dollars or apples in that case. you'd have to generalize and say 8 somethings plus 5 somethings equals 13 somethings. Let's go back to what it's being written right here. If two values don't have the same referent, then numerical addition can be quite unpredictable. For example, can you think of a situation where 1 plus 2 equals 121 makes sense? I'll give you a moment to think about how that might be possible. Pause the video, and then unpause when you're ready. Now, when I wrote this down, that 1 plus 2 equals 121, here's what I was thinking. 1 hour plus 2 minutes. Actually, let me reverse that. I was not thinking that, I was thinking this. 1 minute plus 2 hours equals, since these units don't have the same, or these values don't have the same referent, I can't add them and say we have 3 of something. That wouldn't make a lot of sense. And so, but we do have, if I convert everything here to minutes, right, each hour is 60 minutes, so 2 hours is 120 minutes. So I do have 121 minutes, right? Whenever you say generally that 1 plus 2 is equal to 3, there's an implied assumption about the 1, 2, and 3, and that is that all of them are referring to the same thing, either specific or general. But when they are referring to different specific things, then 1 plus 2 isn't necessarily 3. That's why I say that when two values don't have the same referent, then numerical addition can be quite unpredictable. Number 4, given the operation of numerical addition, the two values being added are called the addends, and the combined amount is the sum. Okay, so in general, we know that 3 plus 5 is equal to 8. So the 3 and the 5 are called the addends, and the 8 is called the sum. Now again, when you write a statement like this, you are assuming that the 3, the 5, and the 8 are all referring to the same thing. They all have the same unit of measure. If they don't, again, you have problems, like 3 cups plus 5 gallons equals 8 what? What would you say? But 3 cups plus 5 cups equals 8 cups. Another way to model addition is to use dots to represent. So there's 3, and here's 5. And when you think of them as separate, you do 3 plus 5, add them together, then all you're really doing is you're pushing these together and forming one new group out of it and saying, well, how much is in the new group? And you would count that we have 8 objects here. But because of the fact that you're just grouping things, it really doesn't matter where this group's from, right? As long as you've got 3 right here and you've got 5 right here, and if you take 5 first and then add 3 to it, you still get 8. If you take 3 first and then add to it the 5, you still get 8. It doesn't really matter the way you add this. So we also know that 5 plus 3 gives the same result of 8. When you're grouping things together, the order in which you group them doesn't really matter. Something to observe. When you have 2 plus 1 plus 4, right? If you have 2 of something plus 1 of something plus 4 of something, right, you have some freedom. You could first group the 2 and the 1 and get 3, and then group that with all of it with the 4 and get 7. Or you could first group the 1 and 4 and get 5, and then add that to the 2 so that you have a total of 7. Or you can rearrange this and say, hey, let's group the 4 and 2 together first and get 6, and then add 1, and that gives us a total of 7. There's lots of different ways that you can combine 3 values into 1. You have some versatility, which means that we could represent 2 plus 1 plus 4 in a few ways that suggest different orders of operation. For example, if you said 2 plus 1 and wanted to do that first, you would put it in parentheses. And this would suggest to the reader that you add the 2 and 1 together first to make 3, and then you group that with the 4 and make 7. Or you could group the 1 and the 4 together first and make 5, and then add that to the 2 to get 7. Or you could use the fact that the order in which you do sums doesn't matter, which we established in the previous operation, and you can move some things around here and do something like this where you group the 2 with the 4 first and then add the 1. Right, there's lots of different ways that you could do this. And let me put little plus signs in this. Equals 1, 2, 3, 4, 5, 6, 7. We get 7 out of this. Here we get 3 plus 4, we get 7 out of it. Here we get 2 plus 5, we get 7 out of this. And here we get 6 plus 1, we get 7 out of this, right? It doesn't really matter how you do this. You get 7 out of each of these approaches. Okay, so what you're seeing here illustrated with addition is that addition is both commutative and associative. The first idea that 3 plus 5 and 5 plus 3 are the same is the commutative idea. So in general, the commutative property states the following, that if you have a value plus another value, then you get the same result as if you switch that around. It doesn't matter how you combine them. The associative property is when you have 3 things being added. And if you do the A plus B first, you get the same result as when you combine the B plus C first. And because it doesn't really matter the order in which you do that, often there are no parentheses written, and you just write this statement without parentheses, and you leave it to the reader to add them up how they want. And that is the associative property. When the ways to remember these is often, these properties often get confused by students the first time they see them. But think of commutative. When you commute, you go from like home to work, right? And then back home. This is called a commute. So if you're going from point A to point B, it's the same thing as going from point B to point A. And this is how I sort of remember that the commutative property is this property here. A to B or B to A. B before A or B before A. Sorry, A before B or B before A doesn't matter. And then the associative property, I think of the word association, which means you have lots of, like an association of people, usually means more than just 2 people. Anyway, it's when you have 3 things added together. The associative property says you could group the first 2 and then add the third, or you can group the second 2 and then add the first, right? It doesn't matter. And when you combine these 2 properties, you get all sorts of things that you could say. For example, I could say A plus B plus C is the same thing as doing C plus A and then adding B. And the fact that these 2 statements are the same, are going to produce the same result, uses combinations of the associative property with the commutative property. Okay, so let's leave this as our official notes. Let me get rid of these little, I don't care that you do these little dots in your work here. But let's leave that officially. Okay, let's look at the next item here, number 5. As learners of numerical addition for the first time, children benefit from using concrete manipulatives to build a conceptual foundation, such as the use of base 10 blocks. Use base 10 blocks to perform the following numerical operations. Now I'm going to actually import, I'm going to import some base 10 blocks that are relevant. We have, I need to import the 10 one and change its size. So that stands for 10. If you're doing this, taking notes on paper, feel free to just draw these representations, right? If you're drawing this by hand, you could do a little block will be a 1 unit. You could do a tall, skinny block that stands for 10. A bigger square stands for 100. And then you can do your best attempt to draw a cube and use that to represent 1,000. Okay. So you can just do those simple drawings to represent these base 10 blocks. But I'm going to go ahead and import pictures of the base 10 blocks. I need to import this one here and make that much smaller. Let's make that one a little bit bigger. Okay, So technically that block there should be the same size as down there. Okay, so we have a 10 block and a 1 block. So when I have 17, I need to do a 10 block with 7 1 blocks. And almost there. I think we're at 6. And you can stack them nicely on top of each other if you want, or you can leave them separate like I've done. But this here is a representation of 17, a 10 block and 7 1 blocks. And we're going to add to this 8. So there's 7, and then let's copy one of those. And we're adding to it 8. So we have this going on right now. Ooh, this is tricky. Okay, I guess I can't move these unless I move them around one at a time. That's unfortunate. Or I suppose I could do this. Oh, anyway. So 17 plus 8. I'm not going to waste your time trying to figure out how to manipulate this iPad or these digital representations of the base 10 blocks. And we're going to group these in such a way the students would grab these and just shove them together and figure out what number they now have. All right, so they're going to take, I think I'm going to have to not do 8 that way. Ooh. Okay, I'm having some struggles here. I think I'm going to just have to do this, make 8 of these the long way. So I need to be able to move them separately instead of that blob of 7. Okay, so this will just take a moment. And do I have 8? Nope, I need one more. Okay, so there's my 8 ones. I'm going to add that to the 17. Now we know that 10 ones put together makes another 10 block. So since I already have 7 ones right there, I just need to take 3 more of these over here. 1, 2, 3. And now I see here that there's 10 ones. And 10 ones just becomes another 10 block. So, gosh, I was hoping there would be a better way than doing it one at a time. I could delete them all at once, but it looks like I can't. So I'm just deleting these all at once, and I'm going to replace them with another 10 block. Oops, that's not what I want. I want to copy it. There we go. And then we can put these all together and see what number we now have. And the resulting amount is we have 2 10s and 5 1s. That is represented by this 25. Now, this might feel very trivial to you, but we are teaching you to become the future teachers of America's children. And so this is how children initially learn ideas about the place values. The fact that you have 2 10 blocks means you have a 2 in the 10s position, and then you have, these 5 1 blocks means you have a 5 in the 1s position. Okay, let's do the next number. And I think I'm going to take the... this is a little more tedious to move these around than I was hoping it would be. Let's consider this 478 plus 653. Okay, so I'm going to insert a few things. We need 4 hundreds. So I'm going to go to my 100 block here. Let's shrink that down. Okay, here we go. We have a 478 and a 653. And we're combining these and want to figure out what the new number is. Well, we start with the smallest denomination first, the smallest unit. That's the ones. We know that every single, when you combine these, when you get a group of 10 of them, it'll make a single tens block. So how many do we have here? We have 8. I just need to move 2 over from here. And that makes a total of 10 right there. So then I would want to delete all that. I think the only way to delete these is to do this, unfortunately. So I'm going to delete these. These become another 10 block, which I'll copy here in a moment. And we get one more 10 block out of this. Okay, so now I see how many 10 blocks I have. Well, we have a total here now of 8 10 blocks, right? The 7 we started with in the 478, plus the one that we just created out of the ones. So there's 7 there. I just need to bring 3 of these up. 1, 2, 3. And we should have now a total of 10 of these. Did I do too few? Oh yeah, I did too many. Now we should have 10. I only had to bring 2 extras up, not 3 extras, because we had 7 plus the 1 that we created from the ones, and then we had the 2 extras. Now I have a total of 10 tens right here. Well, all of that can be deleted and replaced with a hundreds block. So I'm going to take a moment and delete all of these. 1, 2, please delete. Having trouble deleting you. 2, there we go. 3, 4, 5, 6, 7, 8, 9, 10. And those get replaced with another hundreds block. But now we count how many hundreds blocks I have. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I actually have 11 of them, and every 10 of them are going to form a thousands block. So there's 5 right there, and let's group another 5. Okay, so we have a total of 10 hundreds blocks. We can delete those and replace them with a thousands block. So now I'll take a moment and delete all these. And replace them with a thousands block. Alright, so that when all is said and done, right, and the student has all of these blocks and they're putting them together, and they say, what is the final result of this number? And they say, okay, with the rule that you can't have more than 10 of any one shape, right? Because if you do have 10 blocks of one shape, you have to convert them to the next shape up. You can't have 10 or more. You always have to have 9 or fewer of any kind of shape. And so we have 1,000 block, we have 100 block, we have 3 10 blocks, and we have 1 1 block. So 1,131 will be the result of this operation. All right, that's one way that kids will initially learn addition, using things, manipulatives like those base 10 blocks. Once a child has become adept at using base 10 blocks, the child can move on to working with representations that are analogous to base 10 blocks, such as place value tables. So we're going to essentially do the exact same thing we did here, but in a little bit more efficient of a way, but maybe more abstract, less concrete than holding a block in your hand. By place value table, let's take this 17 plus 8. I only need 2 blocks for each number, right? I'm essentially doing 17 plus 8, and I'm going to put an answer down below. 17 has 7 ones and 1 10. 8 has 8 ones and no 10s. So when you combine these together, you have 7 7 ones plus 8 ones, you now have 15 ones, and you have 1 10 plus 0 tens, you have 1 10. And you use this idea that if you have 10 or more in any one box, like the exploding dot idea, if you recall from our last lecture, right? If you have 10 dots in any one box, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you have 10, then you need to grab those 10, move them over as a single dot in the box next to it. So a student recognizes they're not allowed to have more than 9 in any one box, and if they do, then they need to explode 10 of them, so that 15 will go down to 5, and we'll get another 1 put into the tens position. You know, this could also be done with dots instead of numbers. So you could have 1 dot and then 7 dots. And then you say something, okay, now combine that with, let me erase that, make our table a little bit bigger. Combine that with 8 dots in the ones box. And so this is your result. You now have 15 dots in the ones box and 1 dot in the tens box. But you're going to have to take 2 of those, move them down here, and that makes 10 right here. And then make that into a single dot into this box. So I can just delete that and put a single dot here. And so you have 2 10s and 5 1s now. In other words, we just have a 25 is the result of adding this. Similarly here, if you have larger numbers, same idea. We have 478. Let me make that a little bit bigger. We have 4 hundreds, 7 tens, and 8 ones. We're adding that to 3 ones, 5 tens, and 9 hundreds, and that gives us a total of, let's use boxes here. We have 11 ones, 12 tens, and 13 hundreds. And now we, from right to left, we do the exploding dot idea. So we have the fact that, okay, 11 ones needs to collapse to only 1 1, and that makes my 12 tens go up to 13 tens. But 13 tens needs to collapse down to only 3 tens, and the other 10 of those tens made for 1 more hundred, so that goes up to 14 hundreds. But 14 hundreds needs to collapse. We need an extra box here on our table. We need to collapse that 14 down to only 4, and 10 of those hundreds became a single thousand. And so you get this 1,431 is the result of this operation. This is just, you can hopefully make the comparison to what would happen if you had base 10 blocks and you were doing the same thing. Focus on the smallest digits first, the ones, then the tens, then the hundreds, then the thousands, etc. Taking groups of 10 and converting them to a single entry of the next in the next place value as necessary. Now let's compare what we're seeing here with these tables with the standard algorithm. When you're taught to add 17 and 8, you line them up so that the ones are above the ones, the tens are above the tens, etc. And then you add 7 and 8, and you get 15, and you're taught, if you recall, to put, instead of writing a 15 down there, you're taught to do the decomposition of 15 into 5 and 10, and you put that extra 1 up in the tens column, because that really stands for you're adding an extra 10. Although we're taught not to write that 0, although maybe we should, because students think they're adding 1 and 1 and getting 2, and they're just putting a 2 here, and they're not thinking necessarily that that 2 represents 20. So the traditional way is to add 17 and 8, you get 15, put a 5 here, carry the 1 is what they say, and then add the 1 and the 1, you get 2, you get 25. But what's really happening here is you're thinking of the 17 as 10 and 7. and you're adding the 7 and the 8 and getting 15, which you're decomposing into 10 and 5. So the 5 you put here and the other extra 10 you put up there. And then you add those two 10s, you get 20. Right? And so you really just have 25 out of this. And that's really what's going on, right, when you do this standard algorithm. Algorithms should never be taught in place of conceptual understanding. A student should never learn an algorithm first. They should first develop an understanding of addition using base 10 blocks, then an idea of what's happening here in these place value tables, and then finally they can learn this very efficient way of carrying the 1 and adding the 1 and 1 and getting an answer of 25. This process here should be a culminating thing a student does, not an introduction to adding large numbers. You know, the same thing with the algorithm that you would do here, 478 plus 953, right? The algorithm teaches us to add the 3 and the 8 and get 11, but since that's more than 10, you put a 1 here from the 11, and then the 10 you write as a 1, but in the 10's position, which is really a 10, but we don't never write that 0. And then we add everything in this column. Oops, I didn't mean to erase. Right, then we add everything in this column here, which is the 10's column. And we have 1 plus 7 is 8, plus 5 is 13. We put the 3 here and put a 1 here. But really we added 10, 70, and 50 and got 130. So I broke that 130 into a 30, which I put there. And then this one right there represented the 100 part. That's really what's happening here. And now I'm not really adding 1, 4, and 9. I'm really adding 100, 400, and 900 when I add those three. And 100, 400, and 900 make 1400, which when I put a 1, 4 here, because of their positioning, you know, that stands for this is 1400 is 1400. So add that to 31, right, gives us this 1431. Again, I want to re-emphasize that when you're adding this column, you are not adding 1, 7, and 5. You're adding 10, 70, and 50. And when you're adding this column here, you are not adding 1, 4, and 9. You're adding 100, 400, and 900. Sometimes students don't realize that when they learn the algorithm. They just see a whole bunch of single-digit numbers, and that's all they think they're adding, and they have to remember where to put them, and they don't really have a good numerical sense for just how big of a number this represents. That's why these visuals are helpful, because they establish those relative sizes, right? This one here represents this block, and that's much more than just that block, right? So this one here is much more in value than that one there, and working with the base 10 blocks helps children to develop that understanding. That place value matters significantly. You can also use place value tables when doing like binary or base 5 or adding other kinds of numbers. So binary is if you recall, is a situation where if you have, you can either have no dots or 1 dot maximum in a box. As soon as you have 2 dots in a box, the binary says that you want to grab that, move those over here as a single dot, right? You can never have 2 or more dots in a box when you're working with binary. 2 dots become 1 in the next box over. So we have a 5-digit binary number here, so I'm going to need 5 boxes. And we're adding that to a 4-digit binary number. Or if you want to be lazy, you can just do 1 box and put everything in 1 box. So you have a 1, doing the first number first, we have a 1, I'll put it as a single dot, then no dot, a single dot, and then no dot. So here's your 1, 0, 0, 1, 0. And you're adding that to, and let's do this, maybe the next one in red, you're adding that to 1, 0, 1, 1. Right, so that one's in red. And just to be consistent, let's say the first number is represented by the green dots. Okay, then you work right to left, and if you ever see any 2 or more dots in any one box, they need to collapse. So then this would become the following image. So again, make a 5-box table. And we focus here first. There's just a single dot there, so we just keep that single dot. In the next box, there are now 2 dots combined. Well, they will become a single dot, but in the box to the left. So they become this dot. And then in the next 2 boxes, again, there's just single dots. So our final answer is going to be 11101 is what you get when you add these 2 binary numbers. You get this binary number. I'll leave it to you to determine what these binary numbers are. But remember that the first box is how many 1s you have, the second box is how many 2s you have, how many 4s, these are just powers of 2, how many 8s, and how many 16s. Right? So the green number represented 16 plus 2 represented 18, and the red number represented 8 plus 2 plus 1 represented 11. And 18 plus 11 is 19, or sorry, is 29. And let's see, this last box represents 16 plus 8 plus 4, so it's already at 28 plus 1, 29. So we get the same result when we do this in base 10 instead. Right? We get 18 plus 11, and the answer is 29. If we're doing base 5, we have 2 3-digit numbers here, so I just need tables with just 3 boxes. And again, let's do this color coding thing. I like the coloring. So we have a green number here, and then a red number here. So we have 2, 4, 3. Now this is not 243, mind you. This is a base 5 number. So in base 5, this means how many 1s we have here, how many 5s we have here, and how many 25s. We do powers of 5. So this represents the green number in base 10 would be, we have 2 25s, we have 4 5s, and we have 3 1s. So it's really 73. 243 base 5 is the same thing as 73 base 10. But now we're going to add that to 104. So we do 1, then nothing in the 5 box, but then we put 4 in the 1s box. So the red is 104, and we combine these into a new table where if ever you have 5 or more dots in any one box, they must collapse. For example, how many total dots are in this one now? We have 7 total dots here. 5 of them are going to collapse into a single dot and join the 4 that are in the 5 position, leaving only 2 dots left in the 1s position. And we still have the 3 dots over here. But now we have too many here. We have 5 dots here. Those are going to collapse and become a single dot over in the column or in the box to the left. So we have 2 1s, we're going to have 0 5s, and we're going to have a total of 4 25s. Oops. So I wanted to do arrow. Let me go that a little bit higher and a little bit higher so we can write down a final answer here. So we went from this box to this box, then to this box after we did all our collapsing. And in base 5, we have 402 is the result, which is 102, right? Because this really means 4 25s, no 5s, and 2 1s. 4 25s is 100 and 2 1s. So 125 is the answer, but in base 10. 402 is the answer in base 5. Okay, number 7 here. There are various strategies for performing numerical operations, such as numerical addition, such as decomposition followed by recombining or using a number line. Show at least 2 ways to calculate each of the following sums. And here we're not going to be using place value tables or base 10 blocks. I'm going to show you decomposition and number lines as other strategies for combining numbers. For example, let's do a decomposition. If you have 8 of something and you want to add 7 of something to that, you can break up the 7 in such a way that you can make, I'm going to pick 2 and 5, because I know that by the associative property, I can then combine them in this way. I can add the 2 to the 8 first, and that makes a nice clean 10, and then it's easy to add 5 to that, right? And I'm going to create a chain of equal signs, and we get 15 out of this. Another strategy is to use a number line. You start at the 8 position, wherever that is on your number line. And when you add 7 to 8, you go to the right 7 steps. Right, so I'm going to count from 8. 1, 2, 3, 4, 5, 6, 7. Right. 1, 2, 3, 4, 5, 6, 7. We go that way 7 steps. And what number does that take us to? Well, let's actually number these hash marks. We started at 8, and I go over 1, takes me to 9, then go over 1 to 10, etc. And we finish right at this 15. So this is the use of a number line to help get this answer. Another way, this is at least 2 ways, let me show you a third way, or you could start with 8 plus 7 and think of what you need to add to 7 to make a 10, and so break up the 8 in a useful way. So I could break up the 8 as 5 and 3. Associative property allows me to add the 3 and 7 first to get a 10, and then I can just add the 5 and 10 and get a 15, right? So there's a variety of ways to think about this. But decomposition, when I say the word decomposition that you see in bold here, we're talking about decomposing 7 into pieces that make the adding a little bit easier to do in your head. Or you can optionally, as an option, you can decompose the 8 instead. 17 plus 26. All right, I'm going to show you a decomposition where I make 10s and then go from there, and then I'm going to show you another decomposition. So one way to do 17 plus 26 is to ask yourself, hey, what do I need to add to 17 to get it to a multiple of 10? In other words, to get it to 20. And you need 3. So I'm going to leave the 17 there, and I'm going to decompose the 26 into 3 and 23. I'm going to leave the parentheses off because the associative property gives me the freedom to add these how I want. But now I'm going to add the 17 and 3 and get 20. And it's a lot easier to add 20 and 23, and you get 43. Another way that decomposition can be useful is to, let me actually move this like that, is to take 17 plus 26. You could do number lines and sort of represent the same idea. You know, start at 17 and go over 3 first to get to 20, and then go over 43 more. So you could use a number line. I'm not going to do a number line again, but I'm going to show you a different way to do a decomposition. I'm going to break these into their powers of 10 parts. So in other words, I want to think of 17 as 10 and 7, and 26 as 20 and 6. Right, 2 10s and 6 1s. And then you group them by 10s, so you have 30. You group them by the 1s, you have 13. And then if it's helpful to break up the 13, right, you can make that decompose it to a 10 and 3, just leave the 30 the same. You get the idea, and now associative property, I can do the 30 and 10 and get 40, and the 3 stays, and you wind up with 43 in the end. Right, so this is just a whole bunch of decomposition and recombining to get to 43. 9 plus 8 plus 4. One approach is to make 10s. Let's think about what I need to add to 9 to make 10. It's got to add 1 more. So this is the same thing as saying I'm going to take 1 away from that 8 and put it to that 9. So that is the same thing as doing 10 plus 7. And then we have the plus 4. Then I'm going to say I want to make another 10. So how can I break up or decompose this 4 so that when I add it to 7, I get a 10? Well, you decompose the 4 into 3 and 1, and the 7 and 3 make another 10, leaving just a 1 out there. Right, so in the end, you get 21 out of this. Or you could do, we have 9 plus 8 plus 4. You can, a variety of ways, you can take a 1 from the 4 and give it to the 9, so that makes 10 plus 8 plus 3. Then you can take 2 more from that and put it to that 8 and get another 10, so that's 20 plus 1, 21. Right, there's a variety of ways in which you can do these decompositions. And in your notes, feel free to do ones that aren't the ones I'm doing here in this video. But you just have to do at least 2 for each of these. Here's one where you can just rearrange the order. I like this 1 plus 2 plus 3 plus 4 plus 5 plus 6. You could just go in order, right? And just say, okay, here's 3. And then those together, well, let me do it this way. You just add it as they come. 1 plus 2 is 3. Then add 3 to that makes 6. Then add 4 to that makes 10. Then add 5 to that makes 15. And then add 6 to that makes 21. Or you can look at this approach. This is pretty clever. Right, you can add 1 and 6 and you get 7. Notice that if you add 2 and 5, you also get 7. And if you add 3 and 4, you also get 7. So you just rearrange and notice that you get a bunch of 7s. So you just have 7 plus 7 plus 7. And that also gives you, the 21. And now we have 495 plus 331. I'm going to decompose this 331 so that it's easy to add numbers to 495. For example, how much more do I need to 495 to make 500? Well, I need 5 more. So I'm going to essentially do this. I have 495, and I want to pull 5 away from this 331. That makes 3, take 5 away from 31, and you should have 326. Because that's a nice clean 500 plus 326. Oops, and now this becomes very easy to add, right? You're just going to wind up getting 826. One way to do that one. Or you can completely decompose this into hundreds, 90s, and ones, and add that to hundreds, 300, 30, and 1, and group the hundreds, right? Group the tens and group the ones. You group the hundreds, you get 700. Group the tens, you get 120, and group the ones, you get 6. Then if you want, you could decompose that 120 to 120, and then group the 700 and the 800 and get 800. Sorry, the 700 and 100 and get 800. And then we have the 20 and the 6 that come down, right, 826. Okay, so that's all we're going to be saying about addition, at least the strategies and the meanings and the models for addition. Let's move over to subtraction of whole numbers. The quantitative operation of subtraction is the mental act of removing or taking away one quantity from another, or the mental act of comparing the sizes of two quantities. Quantitative subtraction is conceptual and can be imagined even if the quantities are not yet measured. Right? That was the same as for addition. Consider the following statements. John spends some of his money. So let's say this is how much money he has, and you kind of split it down the middle. So you not down the middle necessarily, but you break it into 2 pieces, and then the top piece he spent, so that goes away, and you're left with how much he has left. Right? So you can imagine these quantities changing even if you haven't measured them yet. And that would be something like this. If you have a certain amount and you subtract or minus or remove or take away a certain amount, you get, right, what's left over. So if I were to do some color coding here just to make sure we understand this, let's say the combined amount he has is the orange and the green, and you remove the orange part, what are you left with? Right, you're just left with the green amount. And we would use subtraction as a way to model this sort of taking away. You also might compare John's money with Jill's money. Let's say John has more money, so we'll use a bigger box to represent John's money, and Jill's money is something that's less. And the question is, how much more does John have? Right, so if we were to color code these things, let's say Jill's money is in green, and then if we were to take away that green part and see what's left, that would be the difference. So in other words, we're trying to figure out just how much would we need to add to Jill's in order to make John's. All right, so let's do now just a single color for John's amount of money. Let's say he has red. Jill's money is green. And in orange is the comparison. It's called the difference. Now there's a subtle difference between these two scenarios. In the first scenario here, there's an actual before and after scenario. There's an actual action of taking away. You started with one amount, some amount was removed, and you're left with a new amount. So there's a change to, say, John's bank balance. It's no longer the same. But when you're doing a comparison, we still can use subtraction. I would do John's money minus Jill's money to get the difference. But in reality, there's been no changes to anything. Like John's bank account stays the same, and Jill's bank account stays the same. We're just after a comparison. So there's no physical action of changing numbers in this latter scenario here. This is called doing a comparison of two different values. And again, okay, so here, the first case, there is an action involved. A number gets changed. And in the second situation, no action. We're simply doing a comparison between two static numbers. But in each case, subtraction would be the way to resolve, to answer these questions. Like how much does John have after he spends money, or how much more money does John have than Jill? The numerical operation of subtraction is the removal of one numeral from another, or the comparison of two numerals. So this is where numbers come into play. When I'm talking about quantitative operations, I'm talking about conceptual things. You can think about them without knowing the numbers. You can still imagine things changing or being compared. But the numerical operation is when the numbers show up and you actually do one number minus another number and you get a third number. For numerical subtraction to make sense, I'm at this sentence right here. Notice that for numerical subtraction to occur, the two values must have the same referent. This is the same issue we talked about with addition, right? For example, if I say 3 minus 1, we're used to just saying that's 2. But that's assuming this is only a sensible statement if the 3, the 1, and the 2 all refer to the same thing. Because if I say, hey, what's 3 hours minus 1 day, or minus 1 minute, let's do a minute, then you wouldn't want to say 2 of anything. You'd want to make sure all the units agree and then do the subtraction, numerical subtraction. But you can still imagine removing 1 minute from a time that is 3 days. Like the conceptual operation still makes sense, but in order for you to do a numerical operation and get the number 2, you got to make sure all the units are the same. And this here, John had $8 but spent $3. Or maybe, and then spent $3. And so you would do a subtraction to figure out, take $8 and take away the $3, and that gives them $5 left. All right, notice that all the units are the same. The second sentence says, hey, remove 3 cats from 8 dogs. Well, what does that mean? How do you remove 3 cats from 8 dogs? Maybe this is a nonsense statement. It's not reasonable, doesn't make sense. You can't start with dogs and then remove cats from those dogs. Unless you allow for the possibility of negative cats, which we'll talk about later when we do negative numbers. But if you just have dogs and they say, hey, take the 3 cats away from those 8 dogs, you'd probably scratch your head and say, there are no cats to take away. There's only dogs. Now, if you had changed this to animals and animals, remove 3 animals from 8 animals, then you could say you have 5 animals left. It makes sense to, if you think more generally, instead of specifics of cats and dogs, and think of animals and animals, then you've effectively made them have the same referent, and your answer would be 5 animals. Right, so let's write this. However, 8 animals minus 3 animals equals 5 animals. Okay. You could do that generalization of the units. This is also the first two cases here are this action of removing something, right? A change happened. John had $8, now he just has $5. You had 8 animals, but now you just have 5 animals. So a thing has changed. But in this third case, this is a comparison. Nothing is changing. John has 3 cats, Jill has 8 cats, or 8 dogs. Again, we have the dog-cat issue, so if we go with animals, then we can compare. So I'm going to put AN for animals and AN for animals. John has 3 animals, Jill has 8 animals. Now we can say questions like, well, how many more animals does Jill have? Or how many fewer animals does John have? And you would do the 8 minus 3 and get an answer of 5 animals. And we're doing subtraction to compare the amounts of animals that John and Jill have, even though no animals are being taken away. John still has 3 animals and Jill still has 8 animals. So this is the comparison flavor, and these are the removal flavor of subtraction. Subtraction can also be thought of as the inverse operation of addition. If you want to reverse addition, you should perform subtraction. For example, suppose your bank mistakenly added $100 to your bank account. How would you reverse this? Well, you would then remove or subtract $100 and then get back to what you started with. So it's this idea that if you have some amount of money in your bank, notice I didn't specify, we'll use A, and we'll say it's measured in dollars, and you add to that $100, and that was a mistake, you can then subtract $100 to reverse that, because addition and subtraction reverse each other as long as it's by the same amount. And so this two-step process would take you right back to $8, right? This represents a zero change. In general, it looks something like this. If you have A plus B and then you subtract B, you get right back to A, right? This is what it will look like in an algebra context with variables. Subtraction can also be thought of as the operation to resolve a missing addend addition task. For example, consider the missing addend task below. So you say, hey, I have 3 of something and I add an unknown amount and I get 8. Right? So this is called a missing addend addition task. Right? So if you have 3 of something and then you combine that with you don't know how much, and you wind up getting a total of 8. I think that's 8 there. And you say, how much did you actually add? Well, you could line up the 3 with a 3. In other words, do 8 minus 3. Get rid of those 3 there. And that would tell you how much needed to be added to 3 to get to 8. So subtraction is the operation to help you resolve a missing addend task. The question mark would be, well, the 8 was the total, and remove the 3. In other words, just compare 8 and 3, and that gives you the amount that you needed to add to 3, right, to get to 8. Okay, number 9. Given the operation of subtraction, the subtrahend is subtracted from the minuend to obtain the difference. So if you have a statement, something that says like A minus B is equal to C, this is general, or we can go specific, right, like 8 minus 3 is equal to 5. The first number that in the subtraction is the subtrahend, or sorry, the minuend. Let's just do this. The minuend is the first number in each case. The subtrahend is the second number in the subtraction. So it's minuend minus subtrahend. And then, of course, the result is called the difference. So this difference is the result. These are the terms when you're working with subtraction. Now, we have different words for the subtrahend and minuend in subtraction, but we did not have different words for the two addends in addition. That's because when you're adding A plus B, it doesn't matter what order you do it in. So it doesn't really matter which the ordering. So the name is not significant. You just call it addend 1 and addend 2, and you can interchange them. But in subtraction is not commutative like addition is. We're going to explore that right down here. number 10 here. Does subtraction have the same associative and commutative properties as addition? Consider the following operations. Okay, well 5 minus 3 takes us to 2, but 3 minus 5 is not 2. In fact, if you're already familiar with negative numbers, which I suspect many of you are, it's going to be negative 2. But they're not the same. In other words, 5 minus 3 is not equal to 3 minus 5, so subtraction is not commutative. This is the reason why we have different words for the number that's being subtracted and the number that's being subtracted from, because the ordering matters, so you have different words. Again, the minuend is the first and the subtrahend is the second, and if you interchange those, you do not get the same result in general. Sometimes you do, like if they're the same number, like 2 minus 2, you could argue commutes with itself, but in general, subtraction is not commutative. So we just say overall it's a non-commutative operation. Now let's consider this associative idea, that if you have 5 minus 3 minus 1, in other words, there's a pair of subtractions involved. Strange. I'm not able to write, and I don't know why. Oh, hopefully my pencil is still working for us. Nothing seems to be working. I'm just going to close this app and then reopen it, and it does save, so alright, okay, we're back in business. Good. A little momentary scare. So we do have subtraction twice, and if I force the parentheses in there, the question is, does the order matter? Let's find out. If I do 5 minus 3 first, I get 2, and then I do minus 1, and I get 1 out of this. But if I do the 3 minus 1 first, as indicated by the parentheses, I'd do 5 minus 2, and I get a 3 out of it. So notice I don't get the same thing. So in general, A minus B minus C is not the same thing as A minus and then B minus C first. So subtraction, we say, is not associative either. Okay, so what do you do when you see 5 minus 3 minus 1 and no parentheses? How do you interpret this? We're going to write several other operations that produce the same result, making sure that our operations will demonstrate what's called the distributive property of subtraction. If we just go in order, we just say do 5 minus 3. In other words, pretend like we're going this route essentially. Just go in order, reading left to right. So 5 minus 3 gives us 2, and then we do the minus 1, and we get 1. Oops. That's like starting with 5 things, right? Removing 3 of them first, and then removing 1 of those, and we're left with just 1. So really, in the end, if I started with 5 things, if I remove 3 and then I remove 1, it's not the same thing as just removing 4 from the start? Right? Doesn't that feel like we're doing the same thing? If I remove 3 and then I remove 1, I could just remove 4 from the start. I removed a total of 4. So another way we can say 5 minus 3 minus 1 is the same thing as really just doing 5 minus 4, which gives us 1. We could also think of it this way. 5 minus 3 minus 1 is the same thing as doing 5 minus 4, but 4 is the same thing as 3 plus 1. And so this operation gives us the same result, 5 minus 3 plus 1. But the parentheses have to be around the 3 plus 1, because 3 plus 1 is 4, and then we remove that from the 5. All right, if I don't put parentheses and write this, then this means take only 3 away from 5 and then add 1, and that actually takes us back to 3, which is not what we want. We're trying to find a way to take us still down to just one object, which suggests something. When you have a sum in parentheses, but there's subtraction in front of it, then that's the same thing as removing the parts of the sum separately. Remove the 3 and then remove the 1. This is called the distributive property of subtraction. When you're subtracting a sum, then you distribute the subtraction and subtract the 3 and subtract the 1 both. Right? Removing 4 is like removing 3 and then removing 1. That's the same thing as removing 4. So maybe to answer our question here, I probably don't need to have any of this stuff right here. I can simply say, grab these and say, here are 3 different ways, right, of expressing the same thing. Do 5, then remove 3, then remove 1. That's the first way. That's the same thing as just removing 4 from 5, which you can decompose 4 into 3 plus 1, but make sure it's in parentheses. And then if you distribute the negative, it takes us full circle, right? It takes us back to the original, essentially. So here we see 3 different ways of communicating mathematically the same idea. Remove 3 and 1 separately, remove 4 all at once, or decompose 4 and put in parentheses as 3 plus 1 and think that you're removing that. In general, if a single statement has multiple operations of addition and subtraction with no parentheses to establish the order of operations, then simply perform the operations from left to right. Okay, so in this case here, that's an 11 minus 3 plus 7 minus 5 minus 1. We just go in order. We do that part first. 11 minus 3 is 8. I'll rewrite the rest. Then I do the 8 and 7. Add those together. We get 15. Then I do the 15 minus 5, we get 10. And then finally we do the 10 minus 1, and we get 9. And so we could join all these with equal signs and tell the truth. We simply do the operations left to right when there's no parentheses, and when it's just a bunch of addition subtraction. That's how you should interpret that. Some mistakes people make is they'll insert their own parentheses, like they'll mentally insert parentheses here and say, okay, that's really 10. I'm removing 10 from 11. Well, that's far from the truth. In reality, you just wanted to remove 3 from 11 and then add 7 next. And that's a very different thing than removing 3 or 10 from 11. All right, let's go to next item, item number 11. As learners of numerical subtraction for the first time, the children benefit from using concrete manipulatives to build a conceptual foundation, such as the use of base 10 blocks. Okay, back to these base 10 blocks. Am I going to take the time to copy and paste all these base 10 blocks, or let's do this with just simple drawings like you might do. 35 minus 18. Okay, so I'm going to do the takeaway model, which is what this is suggesting to do right here. Use base 10 blocks to perform the following numerical operations using the takeaway model versus the comparison model. We're going to take 18 away from 35. All right, so 35 is 3 tens. So 3 tens looks like this. And then 5 ones. 1, 2, 3, 4, 5. So there's 35. And we're going to take away 18. All right, so 1, 2, 3, 4, 5, 6, 7, 8. There we go. Now, I want to take 8 ones away from 5 ones. Well, there's not 8 ones there to take away from. So what we do is we take one of these. We're going to take, this 10 right here and break it apart into 10 ones. So it looks like this. So this takes us to this stage. We have now 2 10s and 18 ones. Is it okay? I'm just going to do dots for the ones, and I'll be little boxes. It'll be a little bit faster. All right, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. And so let's do this color coding. Let's make that red, and that's going to correspond to a total now of 18 dots here. What's that? It's 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. So I broke apart this 10 into 10 ones. Now I want to do this same subtraction. And now it's possible. You can just line up the ones. You can take 8 away. Right, so we're going to take these 8 away, and we're going to take one of these 10s away, and then whatever you have here left. Something is not right. I did not do my numbers correct at all. I have to back up here. Sorry for that time-consuming mistake. We had only 5 ones right here. For some reason I put 8. Let's go back and get down to just 5. There we go. Now I have 35 sitting here, and we're going to subtract 18. Okay, so I need to take away 8 ones from here. So let's take those 8 away. And take away 110. And so I just removed 18 from this number, and whatever you have sitting here is what you have left. And that total is a 1 with 7, sorry, a 110 and 7 ones, so 17. Now children usually won't bother using a second pair of blocks like you see here. Or let's just delete that and delete that. Let's put this back up here. So they'll start with a 35 representation, 3 10s and 5 1s, and then they'll be instructed to take away 18. And they'll focus on the 8 part first, and they can't take away 8 1s from 5 1s, so they'll break apart that red 10. So that now that you have really 15 1s, and now that you have 15 1s, then we do the takeaway. And I'm going to put a green circle around what we take away. So we're going to take that away, and we're going to take away, right? Take away a total of 18. So take away 8, and then take away 1, 10. And then that leads ultimately to, we have a single 10 left over, and we have a total of 1, 2, 3, 4, 5, 6, 7, right? These 7 right here are still there. So this gives us a result that the answer is 17. This idea of recognizing that I needed to take away more 1s than I started with, right? I started with only 5 1s, but I needed to take away 8, leads to this breaking apart of one of my 10s. This is the borrowing idea. Like we borrowed from this position right here to make a lot more red singles, so I could take away what I needed to take away. Similar for the 953. All right, so let's go ahead and start with 953, and we're going to be thinking of the 478 by taking away, we're going to take away 400. Right, this is really what's happening here. We'll start with 953. We're going to take away 8, then we're going to take away 70, then we're going to take away 400. So we're working with the 1s and then the 10s and then the 100s, and we go in that order. And conceptually, here's what's happening. Like that's what we did up here, right? We started with the 35, and I first took away 8, and then I took away 10. but I just had to prep everything so that those takeaways were possible. Okay, so let's do something similar, 953. So I'm going to have a total of 900s. So there's 1, 2, 3, 4, 5, 6, give myself more space, 7, 8, 9. So you can imagine the 9 100s being right there. And then we have 50, so we have a total of 5 10s. And then we have 3. So there's 953. We want to take away 478. And we'll do it by first taking away 8, then taking away 70, and then taking away 400. All right, so we got to prep things. There's only 3 ones here. I can't take away 8. So the first stage in preparation, the first step here, is going to be to take one of these 10s and make 10 dots out of it. So I'm going to delete that and put 10 dots here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Now I have enough 1s to take away the 8. Do I have enough 10s left over to take away 70? Well, that would be the next. I don't. I only have 4 10s here. I need to take away 7 10s. So I'm going to have to delete one of my hundreds and make 10 10s out of that. So there's 5 10s. Okay. And then I'm left with only 8 hundreds right here, and I need to remove 4 hundreds of those, and that I can do that. So effectively, I've done this. I've turned 953 into 800 plus 140 plus 13. Right? I started with just the 3, and I had 5 10s to begin with. But I turned one of those 10s, used them to make a 13. That left me with 4 10s, but then I had to get 10 more 10s. So ultimately I had 140 and 800. Notice after this manipulation, what I have, this representation of 953 really looks like this. It's 800s, 14 10s, and 13 1s. And the reason we do that is because now, in order to subtract 478, I'm going to do that in pieces. I'm going to remove 8 from 13, I'm going to remove 70 from 140, and I'm going to remove 400 from the 800. And this makes it possible to do position by position. Okay, so let's highlight the things I'm going to remove in green. Okay, I'm going to remove 8 of these 1s. So let's see if we can figure out how many 8 are. There's 3 plus 5. Is that 8 1s right there? Let's make those green. I'm going to remove them. I'm going to remove 7 of the 10s. I'll make the ones I'm going to remove green. And I'm going to remove 4 of the hundreds. Oops, let's get 4 of them, make sure. I think that'll work. Make those green. Yep. So the green stuff is what we're removing. So I'll put a comment here, remove the green. And then what would be left is in black, right? 13 minus 8 gives me, there should be 5 black pieces left. 5 black singles, right? Those 5 black singles right there are left. I removed 7 of the 14 10s, so that gives me 7 10s left, right? These black 7 10s right there are left. And then I had 800s and I removed 400, there's 400s left. So my answer in the end is 475. And students, children begin to model subtraction by doing this with base 10 blocks and breaking them apart We're decomposing them as necessary so that they can remove enough pieces from the individual kinds of pieces, from the ones, the tens, and the hundreds. Let's make that a little bit lower. And so 475 is our final result. Okay, let's do this kind of subtraction using different kinds of models. Using place value tables, 35 minus 18. So let's first do a representation of 35. This you might find easier to do. We have 35 and we want to remove 18. Okay, well you can't remove 8 from 5, at least not without making negative numbers. So we do this idea of borrowing, right? I'm going to take away one of those tens, make it down to 2 tens only, and make 15 ones there instead. And now, as long as every number down here is lower than the numbers above, now you're prepped to do the subtraction. So we do 15 minus 8 gives you 7, and 2 minus 1 is 1, and so you get 17. Right? This is the first students should work with the concrete manipulatives to do the borrowing, and then they start to use this table to do the borrowing, and eventually we're going to produce the algorithm. Let's do 953. 953 and remove from that 478. And see what we get. All right, so we want, we can't remove 8 from 3, so I'm going to have to reduce that 5 to a 4. So we have 1 less 10 and put that extra 10 right here, so we have 13. So now this number is less than that number, so we can do the subtraction and get a whole number. But I can't do 7 from the 4, so I'm going to have to do something similar. Oops, wrong button. I'm going to have to take this 900s and make them only 800s and throw 1 in front of that 4. That makes 14 tens instead of 4 tens. So that just put the 100 right there in that position instead. And now I can do the 14 minus the 7, and I can do the 8 minus 4, so I'm prepped to just subtract entry by entry. Right? 13 minus 8 is 5, 14 minus 7 is 7, and 8 minus 4 is 4, and we get 475. Okay. And now let's look what the standard algorithm looks like. 35 minus 18. You say, focus on the ones. 8 can't be subtracted. Let me give myself a little bit more space here, too. Let me just delete this. 35 minus 18. Right, we can't subtract those, so you often see the rule is to cross this out, put it one number less, that's the borrowing, and put a 1 in front of that. So we just took 110 away from the tens column and turned it into 10, but in the ones column. And now we're prepared to subtract column by column. 15 minus 8 is 7, and 2 minus 1 is 1. Now, it's super important that you don't go straight to teaching this with a child, because it's too abstract for them still, and they don't understand what's actually being borrowed. They don't understand the significance of the place values. And that when you're doing 2 minus 1, in reality, you're doing 20 minus 10, not 2 minus 1. This is what the base 10 blocks helps students realize, is the magnitude of these, the significance of these place values. And then you can work with these tables, and then the tables turn really easily into these standard algorithm. Right? So when you have 953 and you're subtracting 478, you just do a bunch of what we call borrowing. Right? 8 can't be subtracted from 3 without getting a negative number anyway. So you borrow, make that a 4, and put a 1 in front of there. But now you have, so then you do 13 minus 8, you get 5, and then you move over to the next column, which is the tens, and you're really doing 40 minus 70, what you can't do without getting a negative. So you borrow from the hundreds and make 140. And now you could do 14 minus 7 and get 7, and the last one, 8 minus 4, is doable. You get 475. All right, so again, these procedures here, this standard algorithm, should be something that the students naturally produce on their own by working with this, which is a natural extension of working with something that's concrete in base 10 blocks. Binary, you could do this kind of subtraction as well. So we have 5 digits. I'm going to put zeros in here. We have a 1, a 0, 0, 1, 0. And we're going to subtract from that. Let's see, nothing in the fifth. We do have a 1, 0, 1, 1. I can't subtract this 1 from that 0, so we do borrowing. I cancel that 1, make it a 0, and that turns that into a 2 in binary, right? Because in binary it was going this way, 2 became 1, but going the other way, 1 becomes 2. Now I can't remove this one right here. I can't remove from that 0. And there's nothing here to borrow from, so we're going to have to do a bunch of borrowing here. In fact, let me go back to what the original looked like. Okay, so we're going to have to put a 0 here instead. That results in putting a 2 there. Then I want to take away one of those 2's, make that a 1, and the other one goes into here, making a 2. Then I want to take away one of those 2's, making a 1, and the other 2 go here, making a 3. Then I'm going to take one of those 3's, knocking that down to a 2, and move that over here and to make a 2. So when you, in binary, 0, 1, 1, 2, 2 is the same thing as, of course, this digit wouldn't exist in binary, because in binary you're only supposed to have digits 0 and 1. But as far as value is concerned, it's the same value as 1, 0, 0, 1, 0. Right, because going the other direction, this 2 would become a 0, adding a 1 into here, 3. Well, 2 of those would become, there'd be 1 left, and the 2 of them would lead to another 1 here, making a 2 there, which would 0 out to making a 1 there, which adds to the 1 that's already there, so there's 2, and that 0 is out, putting a 1 there, so you get 1, 0, 0, 1, 0 in binary. Anyway, we just had to manipulate the numbers so that I could actually subtract column by column and do these operations. So we have 2 minus 1 is 1, 2 minus 1 is 1, 1 minus 0 is 1, and 1 minus 1 is 0, and 0 minus 0 is 0. So really, 1, 1, 1 is the result of this binary subtraction. Let's do the 2, 4, 3 minus the 1, 0, 4. This is base 5. So technically we're not supposed to have any digits here that are more than 4. So no 5s or higher. 0 through 4 are the only digits allowed, but we can do some borrowing. And every time I go this direction in the table, a single 1 will turn into 5 more in the box to the right of it, because we're in base 5. So the borrowing would look like this. Let's do the borrowing in red. Maybe this will be easier to follow than the binary, if the binary felt confusing. This will reduce down to 3, and increasing this by 5 to 8. And now I'm ready to do all the subtracting across the columns. Oops, I forgot to deleted that 8 on accident. So now I can do 8 minus 4. Gives me a 4 in this position. 3 minus 0 gives me a 3. And 2 minus 1 gives me a 1. So 1, 3, 4 is the answer in base 5. Mind you, this is not 134, right? This is a base 5 number. It means 125, 3 5s, and 4 1s. All right, there are various strategies for performing numerical subtraction, such as decomposition, followed by recombining or using number lines. 45 minus 19. So let me show you at least 3 ways for each of these numbers. You can decompose these. You can say, there's so many different ways you can do this. You might want to knock the 45 down to a 40. So you say, hey, what do I need to remove from 45 to make it a clean 40? And the answer to that is 5. So I'm going to decompose this 19 into 5 and 14. So it looks like this, but use parentheses. I decompose the 19 to 4 and 15. But then the distributive property of subtraction says remove them separately. Right, remove the 5 and the 14 separately. And removing 5 from 45 gives you a nice 40. I can also decompose the 14. Instead of removing 14, I can remove 10 and then remove 4. right? So if I remove 10 first, I get 30, and then remove 4, and I get 26. Yes. You can do this kind of subtraction. Or you can do, here's another clever way. Removing 19 is like, if you remove 20 and then add 1 back, that's the same thing like removing 19. So you could do this kind of thing. Remove 1 too many, but then add that 1 back. And with this strategy, 45 minus 20 just gives us a nice 25, but then add the 1 back, and we get to the 26 that way. Make sure that looks like a 5. That's a 5 there. This is a common strategy when you're removing something close to a 10. Like, just go ahead and increase that to the 20, and remove 20, but then add back what you need to, so that the end result was like you removed only 19. You can also do, to do number lines on something like this. Let's start at 45. To remove, you go left on the number line. And let's remove 5 first. That's easy to remove because it takes us to a clean number 40. And all the stuff that I remove, I want the total 19. And you're just breaking it up. Let's remove 10 now. Because it's easy to remove 10 from 40. That takes me to 30. And then figure out how much I've removed so far, which is 15, and how much more do I have to remove. I need to remove 4 more, right? So subtract 4 more, and that gets us to the 26th position, right? So number lines, or doing a decomposition and removing in pieces, which is kind of really what happened here as well, but using a number line as a tool. Here's where we removed too much, but then added some back to get to 26. 153 minus 67. You could do similar things here. You can say, okay, I'm going to remove in pieces. I'm going to remove 3 first. So 153, let's remove 3 first. That means I'm going to have to remove 64 later. So that gives me 150 minus 64. Notice what really happened. When you have subtraction, you just remove the same amount from both of these, and you can make a new subtraction. Right? If you just removed 3 from 153 and remove 3 from 67, and then do the subtraction, you get the same difference. Right? That should make sense to you why that's the case. Right? For example, let's say you have 3 and 5. Their difference is 2. That's how far apart they are. But if you extend both 3 and 5 by 1, so it's now 4 and 6, the difference doesn't change. It's still 2. Right? So when you're doing subtraction, and if you remove the same amount from the subtrahend and from the minuend, then you get the same difference. So we can remove 60 from this number and from this number. 150 minus 60. Or maybe remove 50 from each of these. Maybe that's easier to think about. We get 100. Remove 50 from 64, we get 14. Now I can remove 10 and 10 from each of those. So we have 90 minus 4, and then now just remove 4, and we get to 86. This is a clever strategy to do because of this decomposition, ultimately, of that number here, and then removing in pieces is what's happening. Since 67 is not far from 70, right, you could say, hey, this is the same thing as, hey, just go ahead and remove 70, but then put 3 back. And sometimes this is easier, so now from this I'm going to remove 50 and 50. So I get 103 minus 20 plus 3. Now I'm going to remove the 20 from the 103, so we get 83, and then we could add a 3, and then we get to 86. Or you could break these things up into, if you have 100 plus 50 plus 3, and you want to remove 60 and remove 7. And you can do this borrowing idea. All right, so I'm going to knock this 50 down to 40 and increase that 3 to 13. And then I'm going to think of this 100 plus 40 as just a simple 140. And then remove by column. 140 minus 60 is 80, and 13 minus 7 is 6. So if I had 140 and 13, and then I removed 60, and then I removed 7, and then I really just have 80 and 6 that need to be combined, and we get 86. Okay, so lots of different strategies for doing mental arithmetic that are based on decomposition and recombining, and also don't forget distribution of the subtraction. When you're removing a sum, you need to remove the pieces separately. And then, of course, number lines, like you see here, can be valuable tools to a student as well, knowing that you go left on the number line when you remove whole numbers. Okay, number 14. Now we're going to do a few word problems here. Number 14 here is characterize each task as a missing addend or a missing sum addition task. Then resolve the task. Okay, so a missing addend or a missing sum means that the general structure of addition looks like this. And sometimes you know two of these three. Like you might know, the question is, where's the question mark, right? Maybe you don't know A, maybe you don't know B, maybe you don't know C. But if you know at least two of those three, you'll be able to figure out the third. And we're going to use the language of this task to figure out which of the three components of the sum, because we want this to be an addition task, but is it going to be missing an addend or will it be missing the sum itself? Lee has some tickets to a Red Sox game. He learned that his parents would be in town on the day of the game, so he bought 2 tickets for them. Now he has 5 tickets in total. How many tickets did he initially have? All right, so whatever Lee had, you can put a question mark for how much he had. You know that he added 2 to his total amount, and now he has a total of 5. So this I would characterize as a missing addend addition task. And then, of course, we know that the answer is 3. Right. He must have had 3 tickets, so that when he added 2, he would get 5. You can also do like a box for the unknown and write it this way. Students will often see these kinds of worksheets, fill in the missing spot, or you'll see a blank like this, whatever. But in any case, we don't know how many tickets he had initially, but he added 2 to that, and then his total was 5. So definitely this is a missing addend task, addition task. Megan has 3 tickets to the Red Sox game. She is given 2 more tickets by Andrea. How many tickets does she have now? So this is a combining of Megan's tickets with Andrea's tickets. So we had 3 tickets plus tickets by Andrea, and our goal here is to figure out how many tickets she now has. So this is a missing sum. Because we know the 2 addends, we just don't know the sum. Of course, when it's easy to get the sum, we know that the answer is going to be 5 tickets. And by the way, these are word problems, and I want to start building a habit. Whenever you're doing math in a context, you should always have units. Remember what I said earlier in this lecture, that a number without a unit ultimately is meaningless. To say that Lee has 3 without putting a unit on there doesn't mean anything. But Lee has 3 tickets. And in this case, and Megan now has 5 tickets. This case here, Amanda is attending the baseball game. She has 3 tickets. Leon gave her some more tickets because he had to work. Now she has 5 tickets. How many tickets did Leon give her? Well, she had 3 to begin with, and she got some more, but we don't know how much more. But now she has 5. So our structure here is 3 plus something is 5. This is another case of a missing addend. It's the second addend this time that we're missing, and not the first, if that order matters to you. Numerically, it doesn't matter because addition is commutative, but if you want to think of the first one as the starting value and the next one as how much you increased by, and if you insist on that structure, then you could make an argument that when you're thinking about the context, the first number does matter. It has to be how much we started with, and the second number is how much we increased by, and then the sum is our new amount. But in general, with addition, numerically, it doesn't matter the order. But we'll call this still a missing addend. And the question mark here would be, how many tickets did Leon give her? The answer would be 2 tickets. I'm going to go ahead and leave off this question mark equals. And just say our answer is in a box. Right. 2 tickets. And it's really even best when you're answering word problems is to use a complete sentence, which I'm not doing here, but the answer here would be something like, Leon gave Amanda 2 tickets. You know, a complete sentence without using pronouns makes it very clear that you know what question it is that you're answering. Leon gave Amanda 2 tickets. Leon gave Amanda. I'm going to change my mind here and actually write this answer as a complete sentence. And say that's my formal answer of complete sentence with units on my numbers. That's really the best way to answer word problems. Full sentences. You should expect your students to do the same. And the last slide of these notes. We're going to characterize each task below as a missing minuend, a missing subtrahend, or a missing difference subtraction task. Also, we're going to characterize each operation of subtraction as either a takeaway or a comparison task. Then we're going to resolve the task. All right, so Sue had 11 passes to a comedy club. She gave some to Jose, and now she has 8 passes left. So she had 11 to begin with. She gave an unknown amount to Jose, but now the difference is 8. How many did Sue give to Jose? All right, well, this is a subtraction task. We're framing this as a subtraction task because that's what we were asked to do. Frame it as a subtraction task. And the parts that we know are the minuend and the difference. We do not know the subtrahend. So this is a missing subtrahend task, subtraction task. And the way to resolve a missing subtrahend task is to take the difference and add, if 11 minus something is equal to 8, then you want to figure out what needs to be added to 8 to answer this. And so you can just remove 8 from 11, and that would give you that difference. So you can, answer this question here by subtraction of 11 and 8 to get 3. So the answer is 3 passes. And if I remember, do a full sentence. I'm not going to here, but you would say, Sue gave Jose 3 passes, period. But 3 passes is our answer. And we were also supposed to, was this a takeaway or a comparison task? Well, there were only 11 passes total. And 3 of them were removed from Sue. And now Sue only has 8 passes. So this is definitely a takeaway model of subtraction. An action happened and a number changed. Carol has 13 passes to a comedy club. She gave 5 passes to Marcus. How many passes does Carol now have? Well, she had 13 and she took away 5, and now the question is, how many does she have? So we're looking for a difference. This is a missing difference task. And is this a takeaway model or a comparison model? Well, we are changing the number of passes that Carol has because they were removed. So this is definitely a takeaway. And the answer, of course, is 8 passes is how much she has left. And it is a takeaway flavor of subtraction. And as you probably guess what the next one's going to be, a missing minuend, but let's read this. Jim has 6 more passes to the comedy club than Muhammad. Muhammad has 5 passes. How many passes does Jim have? Well, if Jim has 6 more passes than Muhammad and Muhammad has 5, you might be tempted to write your answer this way. You take Muhammad's number of passes, and if you were to add 6 more, you would get how many passes Jim has. So you might frame this as a missing sum addition task. But our goal here, and this would be a fine way to set this problem up, thinking of it this way, but our goal was to set this up as a difference task, not a sum task. And so who has more passes, Jim or Muhammad? Well, Jim does. But we don't know how many tickets he has. So Jim's number of passes minus Muhammad's number of passes should be equal to the difference. This is a missing minuend. We took the person who has more passes minus the person who has fewer passes, and that gives you the difference in passes. And so it's a missing minuend. Task. The answer is going to be 11 passes, right? Because you're saying, hey, what number do I need to remove 5 from to get 6? Well, you can answer that by adding 6 and 5, and we get 11 passes. Is this a takeaway or a comparison? Well, no passes are actually removed. Jim has 11 passes, and he still has 11 passes. Muhammad has 5 passes, and he still has 5 passes. We were simply comparing to see who has more and by how much. So this is a comparison flavor of subtraction. No action was taken, simply a comparison.